Okay. So today we're going to cover a new design pattern, but before we start that, I just figured I would announce that the Builder Lab is live. I'm giving people about a week for that. That's probably going to be pretty consistent through the end of the quarter. We have the Builder Lab, we have the Factory Lab, and we have the Observer Lab as the three that are left to do. And we have just about 3 weeks left to do it. So we're going to be at about a 1 week per lab pace with the project just on the side as well. I figure what we're probably going to be doing on a weekly basis is have something like 2 days, 2 to 3 days of lecture of new design patterns. And then I still want to have a day of practice problems and a day of project working on a weekly basis, just so I can check in with you, see how the project is coming along, get some work done in class. We'll have about one of those days per week, but there's not a ton of content left to cover. Where we'll go over the bridge pattern, the prototype pattern, the observer pattern, and I think I have a couple others planned, but Singleton is planned. Command is planned. So something like 5 more patterns over the course of the next 3 weeks. And that should get us about where we need to be for the class. There are other design patterns. I'll probably take 1 day, 1 or 2 days toward the end of the quarter and just go over, here's a word vomit of all of the other design patterns that we didn't get a chance to cover. And just kind of a high level overview of what they are so that you're aware. But today we're going to cover bridge. Does anyone have any questions about the class or where we are before we get started? I've handed off the exams to be graded. I don't know exactly how long that will take, but I did say that I like to have that week turnaround. So if at all possible, I would like to have the exams back to you by this Friday. That is the plan. All right, this pattern is pretty short, but it's also reasonably important. So let's go ahead and get started with it. So the bridge pattern, we can start thinking about how we hierarchically set up classes to be related to each other. We're familiar now with a couple ways to do this. We can use inheritance or we can use composition. If we think about it though, the abstraction and the implementation are often embedded into that same hierarchy. What that means is we have, how do I want to state this? The hierarchy embeds both of those into that same hierarchy. So if we have some number of abstractions and implementations in our hierarchy, we end up with an exploding number of subclasses as we add additional abstractions or as we add additional implementations, because for each abstraction, we need to make a class based on each implementation. And for each new implementation we add, we need a new class for each abstraction that gets paired with it. So the example that I like to use for this is you can imagine encapsulating into one inheritance hierarchy a color shape combination. So we could have a blue circle or a red circle or a blue square or a red square or something of the sort. If we add a new abstraction, in this case, the abstraction is the shape. Or not, I guess it's the color. One of the two. It doesn't really matter which one's the abstraction, which one's the implementation. The idea is we have a subclass for each combination of these two things. And as we add them, we get a geometric progression. You add one, you have to add 2 new classes. You add one on this side, you add 3 new classes. You add one on this side, you add 4 new classes, et cetera, as you generate more and more and more subclasses. So what we can do about this and what the bridge pattern helps us with is splitting the abstraction and the implementation into separate hierarchies. If we make 2 different inheritance hierarchies, one for the abstraction and one for the implementation, then we can grow either one arbitrarily. We just need some way to compose the abstraction with the implementation. So the solution is to turn both into a separate inheritance hierarchy. Then we need some kind of composition relationship between them so that we see that a shape has a color. So we add a has a relationship between them, and then we can grow and add both new shapes and new colors. So our example, we have an abstract shape class, can be instantiated as either a circle or a square. And boss wants to extend the functionality to add color to shapes. So start small, having blue and red circles and squares. So we need a subclass for each combination of shape and color. So we would have a subclass for blue circle, blue square, and red square. So now, thinking that we have these 4 subclasses, how many classes do we need to add if we're going to now support a triangle shape? We want to extend this to support triangles. How many new classes do we need to create?
For everything or just the triangle?
Just the triangles. We need to add how many classes to our existing 4-class hierarchy. So let me actually draw this out. So we have the ability to make this, I don't know, maybe one with the color. Just gonna dump out all of them. So we have some shape super class. And as a subclass for this, we have a blue square and we have a blue circle. And we have a red square. We have a red circle. And now we say we want to add a triangle shape to this existing hierarchy. We need to make how many subclasses? 2. We need to add a blue triangle. And we need to add a red triangle. And now we've gone from 4 subclasses of shape to 6 subclasses of shape, since all of these inherit from this shape. Great. But now we need to add a green color. How many classes are we adding to be able to support the color green? 3. Now we need a green square and a green circle and a green triangle. So we now needed to add 3. Great. Now we want a pentagon shape. How many classes are we adding to support the pentagon shape? We need 3 more. We need to be able to support some kind of 3, 4, 5. There's no way these are going to be perfect. I don't have that level of artistic skill. Started out like a hexagon and then got wrecked. That one was better. So now we need 3 more classes for that. Now we want a yellow color. How many classes do we need to add? 4. I don't have yellow, so I'm going to go with orange. But now we need a yellow square, a yellow circle, a yellow triangle, and a yellow. How did I do this correctly before? There we go. We'll call that a pentagon. That looks a little bit better. So now we need 4 classes. And now we can imagine, we can see how this starts to grow, kind of like a square. Every time you add a shape, you're adding a row, and every time you add a color, you're adding a column. So it grows kind of quadratically with the size of this. We end up with a geometric progression. So this starts to get gross as you start extending this more and more and more. So the idea is that we can plan for this in advance. If we know that this is going to be extending kind of in this general direction, we're going to be adding rows that are shapes and columns that are colors continuously, then if we planned for this in advance, we could add a single class rather than a quadratic number of classes every time we add something. Rather than adding an entire row or an entire column, we could just add a single class. How could we do that? I spoiled it in the last slide, but what was that solution? What would that look like in terms of a design?
Competition.
Yeah, we have a shape having a color. So now we only have the number of rows, and there's a field that can take one of a number of columns. So shape should only consider the shape. It shouldn't consider the color. So now we're going to break this down into a hierarchy that is shape and color kind of sitting next to each other. And then the shape could be a square or a circle or a triangle or a pentagon. And now a color can be whatever the colors we had were, all of the other colors. A color can be that color. A color can be that color. The color can be this color. I already mixed up the order given what was over here, but you get the idea. We have different colors, and now we have a composition relationship between shape and color. Then when we instantiate a shape, that shape has a color. And now when we try to grow these different inheritance hierarchies, how difficult is it to add a new shape? How many classes do we need to add a new shape? One. Does that new shape support all of the different colors that we've made so far?
Yes.
Yes.
Take out that big colors, please. Exactly.
How many classes is it to add a new color?
One.
One. Does that color work with every existing shape?
Yep.
Yes. So this is much smarter than this because it's going to create a lot less work to expand in the future when you have this kind of a relationship. So this is the concept of those parallel inheritance hierarchies that we talked about before, except that now we're not making individual changes. It's not like when we make a change to the square, we need to make a change over here. It's not parallel. They're separate inheritance hierarchies that can both be grown. Each of them represent a dimension in this two-dimensional chart. Questions on what we've done to make this expandable? It's a lot of design work. That's not really that much work, but it is additional design work. We're trading that off for, as this grows, right here we only have 8 classes, whereas here we already have 16 classes. All right, so now we're going to go through kind of exactly what I've already talked about. So we have shapes. This was the bad idea where a single shape is inherited from by all sorts of, we have multiple dimensions that go into each one of these objects, or the color and the shape. Solution, split the hierarchy by dimension, so we get a shape contains a color. So now if we want to add a new shape, it's just a single class. If we want to add a new color, it's just a single class. There's no modification that needs to be done to the existing classes when we do this. We just add a shape and it plugs and plays. We add a color and it plugs and plays. So this is the idea, but we should go and see how frequently in the real world do people make shapes and colors. Let's go see a more realistic example of this and see how we could apply this concept of the bridge pattern to that. So when we make applications, we very frequently have these components. So one of these components is the graphical user interface. So the GUI is just how we interact with our program. One of them is the back end. So we have how the user is sending and receiving data. We have how we're storing the data, the back end. The back end will do things like figure out how do I need to communicate this in order to interface with Windows or Mac or different operating systems. So we have something like this, where the bridge is now between some framework that supports multiple different operating systems and the graphical user interface. And what we see here is we have two different hierarchies. We have the application with a bunch of different ways of displaying things, and we have a bunch of different operating systems. So we have a hierarchy here, and we have a hierarchy here. So rather than make a GUI, like maybe a mobile GUI design for iOS, a mobile GUI design for Android, a mobile GUI design for something, and a desktop design for Windows, and a desktop design for Apple. You can see how we have suddenly an exploding number of subclasses. It would be much nicer if we could collapse those hierarchies in on themselves and make a bridge where we could add an existing operating system and it would automatically interface with the mobile interface or with the desktop interface. Or we could make an additional layout for the application and say, now you can select that application, that GUI layout for each different operating system. It'd be a way of being able to add different window interfaces and different operating systems in a way that does not break the whole system and doesn't require you to go back and do any work. You don't have to make a bunch of different classes and think about what operating systems do I support? How does this change for how I support those different operating systems? Questions? Does that make sense? All right, another example. We're going to design code for a bunch of different remotes, and each of those remotes will operate a different TV model. This is back before universal remotes were a thing. So we can abstract our remote into an interface or an abstract class, depending on the functionality. It would look something like this, where we have a remote control. And this is back when RCA was a big TV manufacturer. It's great. This book dates itself in so many funny ways. But we have a remote control and we have different remotes for each different brand of TV. And the idea would be that, great, we can control a different TV with a different kind of remote. The issue with this is that this is only the first design of the remote. So it's going to change in the future. How difficult is it going to be to change a particular remote in the future? If we zoom back in on this hierarchy, great, there's an on and an off and a set channel. But now we want to add a Netflix button because Netflix was invented between when this book was written and now. So we want to add a Netflix button to launch Netflix on a smart TV. How much work is it to go add a Netflix button to these remotes?
Can you just add to remote control?
You could add it to remote control, but the way that it works on each different TV, maybe it sends a slightly different signal or it interacts with a slightly different part. So you can add it to the interface, but you need to add it for the implementation for every control that uses that implementation.
Oh.
So we're gonna have to make a modification to every single class in this hierarchy.
And if it's a lot of remotes, nope, that's not a lot of work.
So what's nice in this hierarchy is that if we wanted to add a new remote control for a new TV, how much work is that? It's easy. We just add some third control here, and it's going to inherit all of these things. So we just write all of those methods and then plug and play that into this hierarchy. So this is open for modification, or sorry, it's open for extension on the TV side, but it's not open for extension on the remote side. that make sense? If we want to change something about the remote control, we have to change something about every class that inherits from it. Whereas if we want to add a new TV, add functionality to that, it's very easy, it's plug and play. That tells us that there are two different dimensions in this, which tells us that we could apply the bridge pattern to it, where we have two separate things. We have TVs and we have remotes. So the TV is open for extension, the remote is not open for extension. So what could we do about this? If we just straight up apply the bridge pattern, we end up with something that looks kind of like this. We end up with a has-a relationship between the remote and the TV. The remote has a TV that it controls. So we can add concrete remotes to the remote control hierarchy, and that way whenever we need to add a new remote, we can do so. Whenever we need to add a new TV, we can do so. Does anyone see an issue with this? Yeah,
I don't know about the issue, but is the bridge always gonna be a composition?
yes. So I talked about this. This is one of our code smells. I brought it up moments ago, but here we actually have a parallel inheritance hierarchy. This is what this actually looks like, because each one of these remotes operates one and only one of these TVs. It's not like we can use a Sony remote to operate an RCA TV or vice versa. So each aspect of the remote control hierarchy has a very particular TV that it works with. So because of this, whenever you grow one of these hierarchies, you grow the other hierarchy. So you get this parallel inheritance hierarchy, where there's a big reliance. Whenever you change one side of it, you also must change the other side of it, because they're coupled together very closely. So let's talk about that. First of all, how difficult is it to add a new TV? Simple, you just add a new TV, right? It's going to inherit from TV, so it needs to be able to turn on and off and tune the channel and whatever other methods are there. How difficult is it to change the remote or add a new remote type?
Like blast later, you're done.
It's pretty easy. So this is nice, it decouples the implementation. So now we're not permanently bound to a single interface. We're bound to an interface that makes sense for the extension of what we are. If we are a remote, we want to be able to extend in terms of the remote and not be coupled to the TV as we do so. If we're a TV, we don't want to be bound to the remote. These are two separate concepts that are linked together, so they should be in separate hierarchies. This means that, again, the abstraction and the implementation can be extended independently of each other. We can extend the remotes without affecting the TVs. We can extend the TVs without affecting the remotes. What's nice about this is if there's client code that interacts with this, any change that we make to this does not affect the client code at all. That means that it's not going to break any legacy code that relies on the TVs or the remotes. The detriment is, though, that we did create that parallel inheritance hierarchy. So we talked about some things that we could do if that were the case, to try to decouple that. This is one of those cases where it probably does not make sense to decouple that, because the remote and the TV kind of need to be coupled together, but it doesn't really make sense to try to operate and swap this out at runtime to have a different remote for a different brand of TV trying to operate with the same TV. You're gonna end up with some strange things if that happens. There's a video I really want to show, but I can't.
Why?
It's not appropriate for the workplace. Very funny though. So using the bridge pattern, how do you identify when to do this? Kind of graphic system, graphical user interface, GUI windowing system that needs to run on a bunch of different platforms. You can use the bridge to connect how the GUI communicates with the backend. If you need to vary any kind of implementation and interface in different ways, we need to be able to add abstractions or add implementation independently of each other. The bridge will make a natural sense to this. And you can have more than two dimensions. You can have a composition relationship. One is composed of two, is composed of three. And that allows you to vary three different variables all independently of each other. You can even compose one of two and three and compose two of three. And then you can get more and more complex designs here, but it does scale. A big drawback to this is your code complexity will increase, but your number of classes might not. You might actually be able to collapse the number of classes in the big picture as your application scales. That's really it. The bridge is one of the simpler design patterns I find. You implement them the very kind of the same way. You're just taking multiple inheritance hierarchies, collapsing them, and using composition. It's a pretty simple idea that has a lot of uses out there. But it's just something to be aware of if you come into one of these situations. Does anyone have any questions about the bridge pattern? This is the first one that we have covered that doesn't really have a lab associated with it. It's a little on the simple side for that, but you may find that when you take software engineering, there becomes a time where you have some different graphical systems and some different operating systems, and you want to support that. Maybe in a future game design class, you may find that I ask you to support a bunch of different operating systems, and you want to find a way to make that happen. There may be some future places and some future curriculum where the bridge pattern makes sense to apply. With the remainder of today, I was thinking we could get started on an interesting Project Euler problem that we are not going to be able to solve within the 20 minutes of today's class, but maybe sleeping on it and coming back to it tomorrow, we will have some ideas as well. We'll get started. So let me quickly bring that up. All right. This problem is called maximum path sum. And basically what we are doing is we are taking a triangle and we are trying to figure out the largest sum by moving diagonally down right or down left, starting at the top. So we end up with lots of possible paths if the triangle is reasonably sized, and we want to determine what path do we take in order to get the maximum sum. So for instance, in this triangle that is just height 4, the maximum path sum comes from going from 3 to 7 to 4 to 9. We could have also gone from 3 to 4 to 6 to 9, or 3 to 4 to 6 to 3, or 3 to 7 to 2 to 5. There are quite a few different paths that you could take. In fact, how many paths are there that we could take through that small triangle?
me to say a probably incorrect guess.
Sure.
10.
10? That is an incorrect answer. It's a good try, though.
Too much math.
Computer science is an adjacent to math field. If you're going to be a successful computer scientist, you will need to be a successful mathematician. How many? 24? That is also an incorrect answer. It's a good guess, though. At the first level, how many choices do you have? We could either go here or here. So we have two choices that we could make at this level. Regardless of which path we choose, how many choices do we have? 2. If we're at the 7, we could go here or here. If we're at the 4, we could go here or here. There is no overlap between those. We either have 3, 7, 2, 3, 7, 4, 3, 4, 4, or 3, 4, 6. Each of those are separate. So regardless of how we got here, there are 2 choices at the next level, and this is multiplicative. Regardless of how we got to this level, how many choices do we have? If we're at this 2, we can go to the 8 or the 5. If we're at this 4, we can go to the 5 or the 9. If we're at the 6, we can go to the 9 or the 3. So there are only 8. It's not quite as complicated as it might first seem. But note how each one of these 8 are different paths. We have 3, 7, 2, 8, 3, 7, 2, 5, 3, 7, 4, 5, 3, 7, 4, 9, 3, 4, 4, 5, 3, 4, 4, 9, 3, 4, 6, 9, or 3, 4, 6, 3. So there are 8 things to consider. How many are there in this triangle? So it's the number of rows minus 1, and then it's 2 raised to that power. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 rows. So what is 2 to the 14th power? 6. So 2 to the 10th is 1024. 11th, 2048. 12th is 4096. 13 is 8192. And 14th is 16380, what, 4? There are only 16,384 possible paths through this triangle.
What? That is not small amount.
It is not a small amount to you or me, but it's a very small amount to a computer. So that tells us that we can probably brute force this. What's nice, though, is we can save quite a bit of work by doing this recursively. Because once you get all the way from the 75 down to the 63, how much work does it share in common, whether we look left or right here? Everything all the way down to the 63 is shared in common. So the sum, when we look left or right here, it just depends on what is the sum as we went all the way down to this point. So this tells us that this would be a wonderful problem to use recursion on. You could store the sum seen so far as you move down. When you get all the way to something at the bottom, figure out, is it larger than the largest thing that I've seen so far? If so, output it or store it. If not, when you go back, look right instead of left. Then you look right instead of left. So you're going to keep track of the sum, look left, look right, go back. And that will be going back from the left, so you look right. When you go back from that, you go back. If we were to do this and see this from this perspective, we would do something like, we would see that we look at left, left, left. Then we look at left, left, right. Left, right, left, left, right, 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 left, left, right, left, right, 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 left, and right, right, right. So this is very similar to something like flipping a coin, where you have heads and tails. It's just binary, the direction that you look. So you can model this recursively by saying, output the sum of where you are, look left, look right. Well, you only want to output the sum once you reach a bottom. But basically, you're just going to look left, recurse, look right, recurse, and if you reach the bottom where there's no left or right to move, then calculate the sum. Wherever the largest sum happens to be, that's the largest sum. We have 10 minutes. Go ahead and get started thinking about it. How do we want to internally store this triangle? Potentially. We would need some kind of multi-linked list, though. You could think of this as kind of a 2D array, where at row 0, we have something at index 0. Here we have row, so this is row 0. At row 1, we have index 0 and index 1. At row 2, we have index 0 and index 1 and index 2. This tells us that the successors to a particular, if we start here, we need to look at this index at the next level and the next index at the next level. If we chose this, then we look at the same index in the next level and one more in the next level. If we were here, we look at the same index or the next index. And those are the two possibilities. When you move left, you're just going down one row and looking at the same index. If you're going right, you're going down one row and looking at the index plus 1. And that turns this triangle into more of an array shape that looks more like this. So left is just down, and down right is the right.
There-ish.
Actually,
That was start with five, or at least just grab five. My results just zero. But that's probably just because it's not picking up, but. Great. So, but we can't do that.
So you either want, what I would do, is I would change everything that's up there, instead of char, change that to string. Change those stuff first.
questions on setting this up?
So I just started over it, but I'm just like get it right. So. Making it like a right triangle.
Yeah, so you have a 2D array of size, however many rows you have.
Yeah. I was just gonna start off with the small one, just to see. If I
Yeah.
could, work.
Yeah, so let's make a 4x4 array. 0, 0 should be 3.
Right.
1, 0 should be 7. 1, 1 should be 4. Etc. You're just not going to use the right half of that. This would be even better as a tree structure, but we haven't gone over it in data structures, so I'm not going to go over it as a tree here. We'll just use it as a 2D array for now, and then we can come back to it as a tree structure eventually.
Still, it's.
What is your stack type?
Um,
Yeah.
Stack files.
Should be mostly where you made this.
I'm gonna go. Obviously.
Okay.
Build it fast.
I don't know.
Operator spread.
Oh.